Hi, my name is Arish Virani, and this is my second physics lab on projectile motion. So the purpose of this lab is to observe and predict the two-dimensional motion of a projectile and compare physics-based models to real data. We analyze video track motion, tracker, and build two computational models, gravity only and gravity with air resistance, drag. Using Newton's second law, the momentum principle, measured mass or release position, and the initial velocity from tracker, we compute trajectories, test model predictions against experimental data, and predict final positions of the object. This lets us estimate the drag coefficient b and discuss implications such as terminal velocity and changes in time of flight for different launch conditions. The main result of this lab is that the measured projectile path is well described by a Newton's second law model with gravity and air resistance drag. When all three trajectories are plotted on the same y versus x graph, the gravity-only model predicts a longer range while the gravity and drag model closely follows the data, showing how air resistance reduces height and distance. We observe the effects of gravity and drag on predicted velocity and position. So the physics principles and formulas, Newton's second law defines the net force to be equal to change in momentum with respect to time, or per change in time. We can rewrite this formula to predict final velocity and momentum. The velocity update formula is derived from the relationship of momentum being equal to the product of mass and velocity. The formula can further be rewritten to predict the final position using average velocity, as average velocity is equal to the change of displacement with respect to time. Gravity and drag. Starting from Newton's law, the Earth, mass m, a capital M, pulls on a mass, lowercase m, directed toward Earth's center, as per the first gravitational force formula on the right. Near the surface of the Earth, r is approximately equal to the radius of the Earth. Height doesn't matter, it will always be small enough compared to the radius of the Earth. So we are able to get the value of g, and since r hat points downwards, opposite of y hat when plus y is up, we get the second gravitational force formula on the right. Air resistance is modeled as a force that always points in the direction opposite to the motion of the object, and has a magnitude that is proportional to the square of the object's speed. So for our models and procedure, we recorded a side view video of a crumpled piece of paper, ball, moving across the frame 2D motion. The camera stayed fixed, and a 1 meter rule on the table sets the scale. We analyzed the object's change in position over a period of time using the tracker software. We used relevant data like initial position, initial velocity, change in time per iteration delta t, net force, F gravity plus F drag, mass, Newton's second law formulas for velocity and position updates for GlowScript computational code, and predicted models. We use Excel for graphing both predicted and observed models to compare trends. Finally, we analyze the results and make conclusions from data and trends. So here is the observed model on the tracker software. As you can see in the picture, our system is a crumpled piece of paper, and our surrounding includes the Earth for gravity, air, and the hand or launcher. Our calibration stick is 1 meter. Here's the tracker data, where for comparison's sake, t is equal to 0 seconds at 0.103 seconds in the experimental data, and our final t is 0.4 seconds, which correlates to 0.503 seconds in the tracker data. For the GlowScript computation, the initial conditions are set as such. The mass of the object is 0.0045 kilograms, the initial position is minus 0.13, 0.20 meters, the initial time is 0 seconds, delta t is 1 upon 30 seconds, and the final time is 0.4 seconds. The initial velocity is 4.636, 1.6970 meters per second, and was calculated using the change in displacement over time for the first two values from our data. In our gravity-only model, we are setting the proportionality constant in the drag force formula to 0 kilograms per meter, as there is no drag in this model, whereas for the gravity plus drag model, we are setting it to 0.00185 kilograms per meter. As discussed earlier, we are using the gravitational force, drag force, velocity update, and position update formulas in our iterations for the computational models. This is what we get when we run the code for gravity only, and this is what we get when we run the code for gravity and drag. Here's the graph with the final results, which includes the trajectory of the experimental data, gravity only model, and gravity plus drag model. Assumptions and overall analysis. We are assuming that the motion is perfectly two-dimensional with a fixed camera x-axis on the table, perfectly uniform gravity, and air resistance modeled as a quadratic drag with no buoyancy or spin lift included. We are assuming in general that there are no other forces acting on the object other than gravitational force and drag. The observed trajectory closely follows the gravity plus drag prediction, while the gravity-only model goes noticeably further, longer range, and slightly misses the actual highest point, which is expected because the air drag removes energy. The drag curve sits a bit below the experimental data near the peak and toward landing due to potentially ignoring upwards effects, buoyancy, possible backspin, and a minor bias in the estimated initial velocity. Kinematics agrees here, in the drag model, Vx decreases slowly and Vy drops faster than in freefall. There could also potentially be human errors and errors due to fewer data points in the tracker software for the object or mass. And so our what if and what does it mean discussion. So do any of our models predict a terminal velocity? If the answer is no, what similar experiment could we design to find the terminal velocity of our object? Terminal velocity occurs when the net force is 0 during vertical fall, so speed becomes constant, as you can see in the formula below. In the gravity-only model, the velocity y versus time graph is a straight line with a constant slope, so there is no terminal velocity. In the gravity plus drag model, the velocity y versus time graph does bend towards a potential asymptote. However, our throw doesn't allow that to come to fruition, hence terminal velocity is not reached here either. There is always a net force acting on the object to ensure terminal velocity is not reached. To find the terminal velocity of our object, we can design an experiment where we do a vertical drop of the same paper ball from a much greater height. We can then track y of t and compute velocity y versus time in tracker. When the velocity of y versus time graph plateaus, we get a constant value, which is our terminal velocity. So here, for example, this is shown in the velocity y versus time graphs produced from the computational models for both gravity only and gravity and drag. What if? Imagine if the object were initially thrown straight up with the same initial speed as in our experiment. Would the time this object takes to reach the ground or floor or table be the same, longer, or shorter than that time it took in our original experiment? The time to hit the floor would be longer than in the original angled throw. In the straight-up case, the magnitude of the initial velocity y is larger than in our original experiment. Since TF is increasing in or with initial velocity y, as we have proven above, the straight-up throw stays in the air longer. With drag, drag reduces upward speed and slows the descent, as the straight-up throw puts all of the initial speed into the vertical direction, higher peak, and drag opposes the downward fall. Its total time is still longer than the angled case with the same speed. We are assuming same release height here. So in conclusion, considering the results, the observed trajectory aligns with the gravity plus drag model more than the gravity-only model. Air resistance lowers highest point and range, so the no-drag model overpredicts. There may be small differences stemming from calibration, spin or buoyancy, and time-step error. Our short throw does not reach terminal velocity, and overall, the data confirms Newton's second law with drag for this projectile motion. Thank you.